All right, welcome back everyone to the deep dive. It's amazing how much we rely on these super complex applications every single day, right? I mean, think about it. Social media, streaming, online shopping, it all just seems to work, even with millions of other people using it at the same time.
Yeah, and have you ever stopped to think about how all of that's actually possible? Because behind the scenes, there's this incredible technology at play. It's called distributed systems.
And honestly, getting a handle on distributed systems, that's kind of what we're all about today. Because once you get it, you start seeing it everywhere, and you realize how essential it really is in our tech world. So let's dive into that, right? What exactly is a distributed system?
At its core, a distributed system is essentially a bunch of independent computers all talking to each other over a network. And they're not just chatting, they're working together, coordinating, exchanging messages to get something done, some shared goal they all have.
So, like, the internet itself is a giant distributed system then.
Exactly. It's a perfect example. Now, think about why we would even want to build systems this way. Why all this complexity?
Well, the stuff we've been reading about lays out some pretty clear reasons. The biggest one that jumps out at me is scale. These days, applications have to deal with a truly insane amount of data and users. Like, a single computer just wouldn't be able to handle it.
Right, like imagine trying to run Amazon or Facebook on just one computer. It would completely melt down. It's just not possible.
Okay, so distributed systems, they're essential because of this massive scale. But there's more to it, right? Like fault tolerance. If one part of the system crashes, everything else keeps running. No total meltdown.
Exactly. It's like having backup generators for your data center. Or think about it like this. Let's say you're using a library app.
Okay, I'm following.
So you're on your phone browsing for a book and you click to see if it's available. Behind the scenes, your request goes to the app's front end, then to an API gateway.
That's like the traffic cop, right?
Yeah.
Directing things.
Exactly. Then the API gateway talks to another service, maybe an inventory service, to see if the book is in stock, which in turn needs to get information from the database. But what if the network hiccups while the inventory service is trying to talk to the database?
So it's not just about total outages.
Right. Networks aren't perfect. You could have slowdowns, lost data packets, even hardware failures in routers and switches. And then there's distance.
Yeah, I guess the further the data has to travel, the longer it takes, right?
Exactly. Geographic distance equals latency. Plus, there's only so much data you can send at once, bandwidth limitations, and on top of that, you absolutely need to keep those communications secure.
So from a user's perspective, I might just be staring at a spinning wheel waiting for the app to figure out if the book is even available.
Yep. Or you get some vague error message.
Yeah.
And it's super frustrating because you have no idea what's actually going on behind the scenes.
hmm
But engineers have come up with some clever ways to tackle these problems.
Like what?
Well, you've got network protocols. For one, they set standards so that different systems can understand each other.
Right, like a common language for computers.
Exactly. Then there's service discovery. It's like a directory, helping services locate and connect with each other on the network.
So they can find each other even if things are changing all the time.
Precisely. And a crucial concept is idempotency. This means if a request is sent multiple times, maybe because the network hiccuped, it only gets processed once.
Oh, that makes sense. Like, I wouldn't want to accidentally pay for something twice just because I clicked the button too many times.
Exactly. And to make things even more resilient, systems use things like timeouts, which prevent processes from hanging forever, waiting for a response. Then there are automatic retries, where the system tries to connect again if the first attempt fails.
Okay, so that covers communication, but then there's the whole issue of scaling, like we talked about earlier, and making sure the system can handle more users and more data, and also be resilient so it can handle failures without completely going down.
Right. And those two things, scalability and resilience, they're kind of intertwined. They go hand in hand. Like, back to our library app, what if a ton of people suddenly want to borrow books?
Like after a book signing event.
Exactly. If the app only has one database handling everything, it could easily get overloaded.
Hmm,
And if that database crashes, game over. The whole app goes down.
not good.
So we use a few tricks to avoid that. Replication, for example. We create multiple copies of the database.
So even if one copy goes down, you have backups.
Exactly. And it also helps with performance because you can spread out the read requests across all those copies. But there's more. We also use caching.
That's where you store frequently accessed data in a faster, more easily accessible place,
You
right?
got it. So instead of hitting the database every single time someone wants to see, say, the details of a popular book, you store a copy of that data in a cache. Much faster access.
Clever.
And in a pinch, If a database is down, a cache might even serve slightly outdated info, which is better than just an error message. Then there's sharding.
I've heard of that, but honestly, I'm a little fuzzy on the details.
Sharding is basically dividing the database into smaller, independent chunks and spreading them across multiple servers. That way, if one server fails, only a fraction of the data is affected.
Oh, I see. It kind of isolates the damage.
Exactly. But all these strategies, they definitely make things more complex to manage.
Hmm.
Deciding how to split up the data, making sure the copies are consistent, handling failures, it's all pretty tricky.
It's giving me a headache just thinking about it. And this all leads to another challenge, right? Coordination. If you've got all these separate services, multiple copies of data, different servers, how do you keep everything in sync?
Now you're getting into a really fascinating part of distributed systems. Coordination is key, and it's definitely not easy. Take our replicated databases, for example. If someone reserves a book, that information needs to be reflected on all the copies, right?
Right. Otherwise, some copies would think the book is still available.
Exactly. So one common approach is the leader-follower model. One database is the designated leader, the primary one for writing data. All the other copies are followers, they only read data.
Okay, that makes sense for keeping things consistent.
But then, how do you choose the leader in the first place? And what happens when the leader crashes? You need a way to automatically elect a new leader and make sure the transition is smooth, no data loss or weird inconsistencies.
And what about more complex actions, like, say, renting a book? That probably involves updating the book's availability and then also updating the user's account, right? Maybe even in different databases.
Exactly. That's a multi-step transaction.
Yeah.
How do you make sure both those steps happen reliably, even if they involve different parts of the system? What if one step succeeds and the other fails?
Yeah, you don't want to end up with the book that's been checked out but doesn't show up in the user's borrowing history.
Right? That's where things like distributed transactions come in. And it's not just transactions. All the different nodes in the system need to coordinate on basic things too, like keeping their clocks synchronized, which is surprisingly hard to do perfectly across a network.
I would have thought that was easy, actually.
It's harder than you think. And then making sure things happen in the right order, even when requests arrive at different times. And of course, figuring out if a node has actually crashed, which can be tricky when network problems can look like failures.
Wow, so much complexity. I'm starting to see why distributed systems are such a challenging area. Okay, so we've covered communication, resilience, scaling, and coordination. What else is there?
Well, there's one more big piece, maintainability. Because here's the thing, the bulk of the cost of software, it's not in building it initially. It's in maintaining it over time.
Keeping the lights on, so to speak.
Exactly. And with all this complexity we've been talking about, maintaining a distributed system can be a real nightmare if you're not careful.
Okay, so what can you do to make it easier?
Well, first off, rigorous testing. You need to really put your system through its paces, simulate all sorts of scenarios to catch bugs that might only pop up in a distributed environment.
Makes sense.
Then you need really good monitoring and alerting. You need to be able to keep an eye on the health and performance of all the different parts of the system, spot any weird behavior early on, and get alerts when things go wrong.
So you can fix it before users start complaining.
Precisely. But I'd say the most important thing is to have a really clear, well-documented design, especially when you have multiple teams working on different parts of the system. And documentation becomes even more important as the system evolves over time.
Right, you need a way for everyone to understand how it all fits together, even if they weren't the ones who built it.
Absolutely. And there are even tools that can help with this, things that help visualize and document these complex systems. Okay, so we've spent a good chunk of time talking about the challenges of distributed systems. But let's switch gears a bit and talk about how we actually achieve this massive scale, handling millions of users and tons of data. We've been looking at this example of scaling an e-commerce site.
Yeah, that's a great example. I mean, everyone shops online these days, and those sites have to handle insane traffic, especially during peak times.
Right, and when we're talking about scaling, there are two main things we're trying to achieve. One is handling more and more concurrent requests. That basically means lots of people browsing and buying stuff at the same time.
Right, because everyone wants their stuff now.
Exactly. And the second thing is managing an ever-growing mountain of data, like product catalogs, user info, order histories, all that stuff. So how do we actually scale up?
Our sources talk about two main approaches, vertical scaling and horizontal scaling.
Right, let's start with vertical scaling. That basically means making a single server more powerful. So you might upgrade the hardware, get a faster processor, more memory, bigger hard drives, or you might optimize the software to make it run more efficiently on the existing hardware.
So basically just beefing up your existing machine.
Exactly. And that can work okay for a while for modest increases in load, but there's a limit to how much you can scale up a single server, and upgrading usually involves downtime, which nobody wants.
Right. Taking your website offline to upgrade isn't exactly ideal, so that's where horizontal scaling comes in.
Exactly. Instead of making one server super powerful, you spread the load across multiple servers. Often these servers are actually less powerful individually, but collectively they can handle a much bigger load.
So it's like teamwork. Many hands make light work.
Exactly. And horizontal scaling, it's not just about handling more traffic. It also makes the system more reliable. Because if one server fails, the others can pick up the slack. No more single point of failure.
Ah, that makes sense. Redundancy. So if one server goes down, the site doesn't crash completely.
Right. Now, one thing to think about with horizontal scaling is the concept of state.
State. What does that mean in this context?
It refers to whether a service stores any information about a particular user session. Services that are stateless, they don't store anything between requests. They're much easier to scale horizontally because you can just throw more instances of them behind a load balancer.
So like if a service just needs to process data and spit out a result without remembering anything about the user, that's stateless.
You got it. But things get trickier with stateful services, like databases. Because databases, they need to remember stuff.
Yeah, they're all about storing information.
Exactly. And when you start scaling databases horizontally, you run into some really interesting challenges, like the CAP theorem.
TAP theorem, huh? Sounds intimidating.
It is a bit complex, but basically it says you can only have 2 out of 3 things: consistency, availability, and partition tolerance. And that leads us to the whole question of consistency levels in horizontally scaled databases.
Okay, so consistency. That means making sure all the copies of the data are the same, right?
Right. And there are different levels of consistency. You can have strong consistency where any change is immediately reflected on all the copies. This is really important for things like financial transactions, where you need absolute accuracy.
Right, because you wouldn't want someone to withdraw money that isn't actually in their account.
Exactly. But strong consistency can sometimes be slow and can impact availability. Especially if your database is spread out geographically, there's a delay in getting the updates to all the copies. Then you have eventual consistency, where there's a bit of a delay before changes are reflected everywhere. This can be faster and more reliable in terms of availability, but it means that different users might see slightly different versions of the data for a short time.
So, like with social media, if I post something, it might take a few seconds for everyone to see it.
Exactly. It's a trade-off. You have to decide what level of consistency is right for your application. So we've talked about the concepts, but how do you actually do horizontal scaling in practice? Well, one technique we've already mentioned is load balancing. You basically have a traffic cop that directs incoming requests to different servers, making sure no single server gets overloaded.
Okay, so you're spreading the work evenly, but what happens when the amount of data itself becomes too much to handle even with multiple servers?
That's when you need to look at data partitioning or sharding. Remember our library example?
Yeah, where we were splitting the database into smaller chunks.
Exactly. But there are different ways to do that splitting, different ways to partition the data.
Like what?
Well, you could split it vertically, where you separate data based on different features or functions, or you could partition by value.
By value, what does that mean?
So, for example, you could have one set of servers for users in North America, another for Europe, another for Asia, and so on.
Oh, I see. So you're grouping data based on some criteria.
Right. And then there's hashing.
Hashing.
You basically use a special function to assign data to different servers. Like you could use the user ID to determine which server their data goes to. And there's a more advanced technique called consistent hashing that helps minimize data shuffling when you add or remove servers.
Okay, my head's spinning a little bit, but I think I'm getting the general idea. So we've got load balancing, sharding, and then there's replication, right?
Right. Replication is all about having multiple copies of the data. And this is especially useful for applications where you do a lot more reading than writing, like, say, a news website.
Because you've got way more people reading articles than writing them.
Exactly. So with replication, the read requests can be spread across all those copies, making things faster. And it also provides redundancy, so if one copy goes down, you still have others.
So if we put all this together, a really horizontally scaled e-commerce site, it might have multiple application servers behind a load balancer, and then a database that's split up using sharding and replication, all working together to handle all that traffic and data.
You got it. That's how these sites handle millions of users. But of course, there are trade-offs.
Like what?
Well, for one thing, horizontal scaling can be more expensive because you need more servers. And communicating between all those servers, that adds latency.
Latency, that's the delay we talked about earlier.
Right, so you're distributing the workload, but you're potentially introducing more delays in the process.
Makes you wonder how these sites are still so fast. And that leads perfectly into our last deep dive for today, which is caching for performance.
Right, because if distributing our system can make it slower, we need ways to speed things up again. And that's where caching comes in. Basically, it's all about storing frequently accessed data in a faster, more easily accessible place. So instead of having to go all the way to the main database every time, you can grab the data from the cache much faster.
So it's like keeping a copy of the most popular books right at the front desk of the library.
Perfect analogy. Now, there are different types of caching. You have CDNs, which are content delivery networks. They're basically networks of servers that store static content like images, style sheets, and scripts closer to the users.
So when I visit a website, those static files can be downloaded from a server that's geographically closer to me, making things faster.
You got it. Then you have in-memory or local caches. These reside directly on the server where a service is running.
So very quick access for that particular service.
Exactly. And then you have distributed caches like Redis or Memcached. These are separate systems that sit between the application servers and the main database.
So multiple services can share the same cache.
Exactly. And it's important to remember, caching can be used at different layers of a distributed system, making it a very versatile tool for boosting performance. But it's not without its challenges. Our source quotes Phil Carlton, who famously said, "There are only two hard things in computer science, cache invalidation and naming things."
Cache invalidation.
It's all about figuring out when the cache data is no longer valid and needs to be updated or removed. Think about our e-commerce example again. If the price of a product changes, but the cached price is still the old one, that's a problem.
Yeah, you definitely don't want to be advertising the wrong price.
Right. So you have to figure out how often to invalidate the cache.
Yeah.
Too often, and you lose the performance benefits. Not often enough, and you end up with outdated data. And then there are cache misses.
Cache misses.
That's when you go looking for data in the cache, but it's not there. And this can be a problem in a horizontally scaled environment with a load balancer. Imagine you're shopping online and you add an item to your cart. Now, in a horizontally scaled system, your requests might be handled by different servers each time, thanks to the load balancer.
Right, the load balancer is trying to distribute the workload evenly.
Exactly. But if each server has its own local cache, when you go to view your cart, you might end up on a server that doesn't have your cart data cached.
So a cache miss. And the server has to go fetch the data from the main database, which is slower.
Exactly. And if this keeps happening, because you're constantly being routed to different servers, it can really impact performance. So designing a good caching strategy, it's not as simple as just slapping on a cache.
Sounds like there are a lot of things to consider.
Definitely.
Yeah.
You need to think about what data to cache, how long to cache it for, how to invalidate it, and where to implement it. And it gets even more complex when you have multiple layers of caching.
So caching, it's something you have to plan for carefully. It's not a magic bullet.
Right. It's a powerful tool, but it's often something you tackle later on after you've dealt with the core issues of maintainability and scalability.
Well, this has been a fascinating deep dive into distributed systems. We've covered a lot of ground, from the basic reasons for building these systems, to the challenges they present, to the techniques for scaling them up, and finally, the role of caching.
It's amazing how complex it all is.
So as our listeners think about all this, what's the one big takeaway you'd like them to remember?
Well, I think it's important to realize that there are always trade-offs when designing distributed systems. You have to consider the CAPI theorem, the balance between consistency, availability, and partition tolerance. And you have to think about what's most important for your specific application and context.
Right. There's no one-size-fits-all solution.
Exactly. And that's what makes this field so challenging and so fascinating, because it's not just about the technology, it's about understanding the problem you're trying to solve and then finding the right balance between all these different factors.
Great stuff. Well, on that note, thanks to everyone for joining us on the deep dive. We'll see you next time.